Hey everyone! Today we're going to pull back the curtain on artificial intelligence and look at the powerful, kind of hidden engine that makes the whole thing work, optimization. Now, I know it's not the flashiest part of AI, but trust me, without it, machine learning would just stop.
And that's because, when you boil it all down, that's what machine learning really is. It's this relentless, non-stop search for the lowest possible point, the point where the error is as small as it can possibly be. Okay, let's get into it. To really wrap our heads around this journey to the bottom, we're going to use a pretty cool analogy. Think of it as a hiker's guide to something called the lost landscape. We'll start with the search itself, then talk about how algorithms actually navigate this landscape. We'll get into the big trade-offs, speed versus precision, the surprising power of just keeping things simple, and finally, how you'd pick the right explorer for the job.
So first things first, the search for the best. And at its heart, it really is just a journey to the lowest point you can find. Machine learning can feel like magic, but it's not. It's really just a search. A model is defined by tons of numbers or parameters. The best way to think about them is like millions of tiny little dials. Optimization is just the process of turning all those dials, trying to find that one perfect combination that makes the model's predictions as accurate as possible, which of course means finding the combo with the minimum possible error, or what we call loss. Okay, so let's build on that search idea and get to our main analogy, navigating the lost landscape. In this world, every single algorithm is like an explorer, and each one has its own special strategy.
This whole idea of a lost landscape makes a really abstract concept feel, well, real. Just picture this vast mountainous terrain. The elevation, how high up you are, represents your model's error, and your location, your coordinates on the map, those are the settings of all your model's little dials. So what's the goal? For our algorithm, our little explorer, it's to find the absolute lowest valley in that entire landscape.
So our explorers have two basic ways to get down the mountain. First, you've got the methodical surveyor. This is batch gradient descent. This hiker looks at the entire map, all of the training data, to calculate the absolute perfect, most direct step downhill. Then you've got the impatient trailblazer. This is stochastic gradient descent, or SGD. This hiker, they just glance at the tiny patch of ground right under their feet, just one piece of data, and immediately take a step in whatever direction looks steepest.
And right there, that's the crucial point. There's a massive trade-off. The surveyor's path, it's smooth, it's direct, it's guaranteed to go downhill. But it is incredibly slow and needs a ton of memory. Can you imagine needing a map of the entire planet just to take one single step? It's not practical. The trailblazer's path, on the other hand, it's noisy, it zigs and zags all over the place, but it's lightning fast and works on these unimaginably huge landscapes. And that is why it's the absolute workhorse of modern deep learning.
But it's not just about how much of the map you look at. It's also about the kind of tools you're using to read it. And this brings us right to speed versus precision.
Okay, so our basic hikers, they're using what we call a first-order method. All they can do is feel the slope right under their feet. That's the gradient. It tells them which way is down, but it doesn't tell them anything about the shape of the valley. A more advanced explorer, though, they might use a second-order method. Think of this as having a full-on topographical map that shows the curvature of the land. That's called the Hessian. It lets you take a much more direct, intelligent path to the bottom. But, and this is a big but, calculating that curvature is computationally very, very expensive.
And that kind of makes you wonder, with all of the messy, noisy data we use in machine learning anyway, do we even need that kind of precision? Is finding the absolute, mathematically perfect bottom of the valley even the right goal to begin with?
This really gets to the practical reality of it all. The data we use is imperfect, it's got noise, it's got errors. So because of that, like the authors of Optimization for Machine Learning point out, trying to find a perfectly precise, mathematically exact solution is, well, it's often a waste of time. A good enough solution is usually all we really need. And that insight, that good enough is often what we're after, leads us to our next really big idea, the power of simplicity. Because sometimes the best answer isn't just about finding a low point, it's about finding a simple one.
We make this happen with a technique called regularization. The easiest way to think about it is we're adding some new rules to our hike. We add a penalty to our error score for being too complex. This encourages our explorer to avoid those really complicated, jagged paths and instead find a valley that's not only low, but also smooth and simple. One that will probably work way better on new parts of the landscape it's never seen before.
And there are two really famous rules our hiker can follow to help enforce this kind of simplicity.
The first one is called L2 regularization.
And the rule here is pretty straightforward. Don't take extreme routes. What it does is penalize models for having really large parameter values, those big dramatic turns of the dials. This pushes the model towards a solution where all the parameters are pretty small, which leads to a smoother, more stable model that's way less likely to overreact to every little bit of noise in the data.
The second one is L1 regularization, and its rule is stick to the main roads. Now, here's where it gets really interesting. The key difference is that L1 doesn't just shrink parameters down. It can force some of them to become exactly zero. So in our hiking analogy, it's basically telling the explorer to completely ignore certain paths, which effectively simplifies the entire map.
This effect, it's called sparsity, and it's an absolute superpower. When you're dealing with a landscape that has millions of dimensions, like a model with millions of different features, most of those dimensions are probably just noise. L1 regularization acts like a built-in feature selector, automatically zeroing out the useless paths and forcing the search to focus only on what truly matters. It's a game changer.
Okay, so let's try and put all of this together. How do you actually pick the right explorer and the right strategy for your particular journey?
Well, it really just comes down to a few key questions. First, you've got to assess your terrain. Is your landscape built from a massive data set? Then you absolutely need the speed of the trailblazer, a stochastic method like SGD. Second, define your mission. Do you need a simple model where you can actually see which features are the most important? Then you'll want to apply that stick to the main roads rule of L1 regularization. And finally, check your resources. If you've got tons of computing power and maybe a smaller, well-behaved problem, then maybe, just maybe, you can afford to map the curvature with a second-order method. At the end of the day, it's all a game of trade-offs.
Which brings us to our final thought. The lost landscapes of today's biggest AI models, they're not just mountains anymore. They're astronomically complex, high-dimensional, and frankly, we don't understand them very well. The simple explorers we've talked about are still the foundation, for sure, but the search is on for new, much more advanced strategies. So the real question becomes, as these landscapes grow ever more alien, what new kinds of explorers will we need to invent just to find our way?